Good afternoon, everyone. Today we are in the new topic, actually the continuation of what we were having yesterday's lecture about the simulation of business systems and how can we use simulation to study business systems. You might have already seen that we have worked on multiple topics about the simulation and introducing to you the language of simulation, various concepts of it. And today we will further go deeper into the topic, and so that you can understand the individual modules of simulation systems and how can you use such modules to build a simulation model of a business system. So, if you look at the learning agenda, we have already seen that we have studied the nature of simulation in the previous lecture and the brief history. These things were covered in the first lecture. Okay. Then systems, models and simulation, the applications of it, real world applications, and why simulation is needed, the advantages, disadvantages, this all we covered in the second lecture. Okay. Now, today we will focus more towards how to build simulation models. That kind of a question we will try to identify, and the examples we will work on the next class to actually demonstrate how an actual simulation works by hand and why it is intractable to do large simulations using hand. You require a computer to do that. So, first we will get into the concept of type of systems or types of system. Yeah. And there is in for the people classify, again this is different. Please remember this. This is different from the systems engineering approach. Systems engineering approach. So, we are talking about business systems here, and business systems generally we are trying to create into what we call as a using simulation to study those systems. So, for us there are mainly two types of systems. The first one is the discrete system and the second one is the continuous system. Okay. So, what is a discrete system? Discrete system is a system where system state variables change instantaneously please check my spelling, I am not very sure about my spelling, instantaneously at separated points in time. So, the remember we studied what is a system state variable. These variables, what are they? They describe the state of the system, at any given time. That is a system state variable. So, these state variables they change instantaneously at an instant, they change like this quickly at separated points in time. Okay. We will give an example is a bank teller operation. Okay. And remember we looked into some of the system state variables, and if we use one of the system state variables is number of people in the system. Okay. This is equal to number of people waiting in queue plus number being served by the teller. If you imagine a bank teller, here is a bank teller and people are waiting in a queue in front of the bank teller. These are all individuals, okay, waiting in a queue, and there is one person being served, okay, or maybe two people being served, it does not matter. So, then the total number of people in the system is the people who are waiting in the queue, this one, and the people who are being served, sum of them. So, if you plot that in a graph on a time scale t, At initially when the time t equal to 0, and if you say here as the number of people as the y axis, initially the value will continue to 0 for some time, and at a particular point when one person arrives, this number will go to 1. So, here you have 1, 2, 3, 4, 5, 6 like this, and then it will continue, and then one person more arrives, it goes to 2, continues, and at some point of time this first person service gets done. So, it goes down to 1, and then it continues like this for some time, and then maybe another arrival happens, then it goes to 2, then it goes to 2, and then remains for some time, then another arrival happens, goes to 3, then it comes down to 2, then it comes down to 1, then it continues like this. Okay. So, this depends upon this changes when a person arrives or leaves the system. So, these are all these things that you see, they are instantaneous changes. Only at a particular instant the system state changes, and then it continues in the state for some time, then it changes again. Okay. So, such type of systems are called as discrete systems for the purpose of simulation. So, then and what would be a continuous system? Continuous system will be something where system state variables change continuously as a function of time. Okay. One of the examples of this would be flight of an aircraft. So, if you think about it, if you think this is being the runway, okay, and then here is an aircraft standing here, okay, just its wing, okay, it's ready to fly, and this is the runway, okay, and then it flies, then from here it takes off, and it flies to some level, then it again flies to some level and continues, and then it descends to some level, continues, and then descends, and then here is another airport where it finally comes and lands. Okay. So, if you think about it, and here is time, okay, continue. So, at every instance of time the aircraft is doing something, things are changing, it is not instantaneous. Even if it is gaining altitude, once it takes off, let us say this is the takeoff point. Okay. From here, let us say this is, let us say first ceiling or something like that. Okay, let us say 20,000 feet or something. The aircraft does not go from 0 feet to 20,000 feet in like instantaneously. It takes time to climb. Okay. So, this is the continuous variation. Similarly, then it might continue in 20,000 feet for some time, then it will go to maybe 32,000 feet. Okay. So, this will be the second set of climb, then this would be probably it will stay in its cruise altitude, okay, and then from here it may come down to the one altitude, let us say 10,000 feet, okay, and then stays in this, then maybe come down to the 5,000 feet, okay, and then it comes and lands, something like this. So, all these changes, okay, you can see that these are not instantaneous, but a function of time. Okay. All these changes, okay, these changes, they are all functions of time. So, such kind of a system where the system state variables change continuously as a function of time, and this is important because this kind of systems are also simulated. For example, autopilot simulations, okay, they include studying such kind of continuous systems. The only difference is that mostly in this course we will be focusing more towards discrete based like systems, because we are more interested in discrete systems rather than continuous systems. We will only look at few examples of continuous systems in the class, and in realistically many systems are partially discrete and partially continuous. So, for example, is time continuous or discrete? Okay. So, this is an interesting question because time by rule is continuous. Okay. So, you can say theoretically time is continuous, but the watch that you wear, you can only measure the time in seconds. So, most watches allow time measurements in hour, minute and seconds, okay, not the other values. Why? Because for easy usage time has been discretized. Because discretization allows us to study the systems quickly. Okay. So, that is why we actually discretize time. So, if you look at your watch, you will see that the seconds clock tick, 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 and that tick is by the seconds. Okay. So, that is what happens. So, I hope you will now understand the concept of what is called as a discrete system and what is a continuous system. And as I said earlier, we are going to focus more towards the discrete systems. Okay. So, now the second question is, the next biggest question is, how do we study a system? What are the ways in front of us is to study a system? Again, as I want to remind you guys, here we are focused on system simulation, not systems engineering. Okay. So, we are going to study how we are trying to find out how we are going to study a system. So, let us assume that this is a system that we want to study, a system. So, we want to study this system. Let us assume that we want to study this particular system denoted by. There are two ways we can do it ideally. Okay. So, there are two ways. The first option is to make a big rectangle, experiment with the actual system. Second option is experiment with a model of the system. Okay. So, assume that you have a car manufacturing facility. Okay. Let us say for example, automotive manufacturing. Let us say we are interested in manufacturing of cars, four-wheelers. Okay. So, one way to do it is actually do the experiment with actual factory. This means do experiment with actual factory. Okay, this sounds good and this is probably the best way to do the experiment, but this has its own inherent disadvantages. What are those inherent disadvantages? Number one, too expensive. Nobody will give you a factory to play around with. Okay. Second one is, anything goes wrong, too risky. And the third one is adversely impact productivity. impact production. The job of a factory is to produce cars. This car manufacturing factory, the aim is to produce cars, not to allow you to conduct experiments with the system. So, because of this expense and the riskiness and the adverse impact on the production, this approach, okay, is not preferred in industry. Well, if you want to try a weapon, then as you do how to make a weapon and then drop the weapon and find out how the weapon is. But if you want to study about a factory, it is almost impossible for you to expect that the factory will come to you, somebody will give you the factory to do the experiments. So, the second option is experiment with a model of the system. So, here also we have two options, ideally speaking. Okay. The way to do this is, first is to build a physical model. Okay. Physical model is like a model of the system which has how do you put it, like for example, if you are building a car, okay, so some people will say, okay, I will take clay, like if I draw something like this, it does not look like a car much, but if you see something like this and then put 4 wheels on it, then you will say, oh, this looks like a car. So, I can actually make a physical system of this also. I can make it in using the actual materials and build a physical model of it. Other option is I can build a mathematical model of it. Build a mathematical model. So, I can say that the mass of the car is equal to 1,000 kilograms, and I want to accelerate it at 2 meter per second or something like this. Then I can find out how much of force is required using the mass into acceleration and something like that. So, then this mathematical model will be applicable to car, jeep, motorcycle, bus, whatever it is. So, these kind of systems is called as a mathematical model. So, you mathematically represent the system. Okay. Then in the mathematical model again you have two options. Okay. So, I am kind of drawing it little far away. The first option is to build an analytical solution, okay, and other option is using the simulation. Okay. So, using an analytical solution is by known methods of mathematics. Okay. So, an example of this would be, one way to think about it is, what would be the best example to do? Okay, here. So, let me give you a simple example. You want to, let us say here is a gun with a howitzer and here is a target, okay, and you want to find the angle theta at which you need to fire, so that it will come and hit the target. Okay. So, if you know the force with which the projectile comes out, then you need to find out E is known. If you know that, then you know what is this distance, okay, and then using this you can find out at what angle you need to fire, so that the projectile will reach this particular distance, so that you can hit the target. Okay. So, you can solve for the theta, and then you are able to identify, okay, it is you fire at 38 degrees, then you will be able to hit this target or something like this. Okay. So, this is the analytical approach. In a simulation, it would be a numerical approach. So, what you could do, think about it is, you can say that, okay, here is the gun, and here is the barrel. Okay. Then you can say here is the theta, and then you will say I will start with theta equal to 10 degrees, okay, and then find what is the distance. So, let us say, let us assume that the distance equal to 20 kilometers, okay, and then you find out that it reaches 17 kilometers, okay. Then theta equal to 20 degrees, you find out that it reached 18 kilometers, and that is a theta equal to, I am just giving you an example, 30 degrees, it reached 19.2 kilometers, and theta equal to 40 degrees, then it reached 20.4 kilometers. So, now you know that the desired angle is somewhere between 30 and 40, okay, and then now you can basically figure out, okay, it's 40, 20 is close to this. So, I might start reducing from 40. So, I might do now 39, then I do 38 like this. Okay. So, this is one way of numerically studying the system. You are trying to simulate the behavior of the system for different ranges, different thetas, and then find out which one would actually work for it. It is kind of same way. What you actually do is, simulation is you provide scenario and measure the output. And then once you have many such outputs, then you find the average of outputs, okay, and then you use these averages. I am just giving you a broad example, but what you are looking at is, you are looking at the, what is something called as the expected value of the parameter is what you are looking at some point of time. You will see what is an expected value and all those aspects little later down the road, but for the time being, I hope this will give you a rough idea of how the simulation and analytical model actually works. Okay. Now, from here, let us look into what we call as the classifications of the simulation model. Okay. Most of the simulation models that are built for studies are classified into multiple options. The first classification is static versus dynamic. Okay. So, static model means, model implies the state of the system does not change as time progresses. Okay. So, for all practical purposes, the system remains constant, there is no change in it. So, an example of this will be a clay model of the car. Okay, you built it, and then once you have frozen the design, it just stays there, nothing is going to change. Dynamic model, on the other hand, what happens is, the state of the system changes over time, or as time progresses, system state changes. This change can be either instantaneous or it can be continuous. Okay. It does not matter. The important thing is, as time progresses, the state of the system changes. Okay. That is the most important. Second type of a classification is what we call as deterministic versus stochastic. Okay. So, a deterministic model means, deterministic model implies there are no uncertainties associated with any state of the model. Okay. How do I put it is that there are no probabilities. you know that is what is going to happen and that is what it is. There is absolutely no probabilities that are associated with it. So, the system is deterministic. Okay. On the other hand, stochastic model implies the state of the model, state of the system, okay, is not known with, this is the most important thing, not known with certainty, or it implies that every system state has a probability. Okay. So, there is a probabilistic occurrence associated with every system state. Okay. Such kind of a system, such kind of a system, that a model that makes such a system is called stochastic model. Okay. So, there is one option is deterministic and stochastic. Then the third one is continuous versus discrete. We have already discussed this. So, discrete model implies state change of the system. If the system changes are, which also means that is also applicable to the model. The state change of the system or the model happens only at discrete time instances. Okay. Or in a way that, or you can think about as the happenings in the system are countable. Since it happens in discrete instances, you can start counting it now. Okay. Whereas continuous is the opposite of the same. Okay. State change happens continuously over time, which implies not countable. Okay. You are not able to count what is happening over time in the system. So, hence for our course mostly, most of the operational models, most of the models that we are going to study, these operational models in this case we are talking about is the business systems. Okay. Most of the business systems for which we build operational models are dynamic. Dynamic means the state of the system changes as over time. So, the system will change so we will say it as state of the system changes over time. Then this is also stochastic, which means probabilistic. There is a probability component, probabilistic behavior. So, the system occurrences, different aspects of the system or different states of the system are not known for certainty, but the occurrences is associated with a particular probability. Discrete means the system is countable. Okay. Countable or countably, finite or infinite. So, it happens at specific instances of time, and those instances or occurrences are countable as far as we are concerned. Okay. So, what? So, now in our case, hence we actually study more on discrete event simulation models. The right phrase for this is actually what we are going to study is what we call as, I am just going to write it here, discrete event stochastic simulation models. Okay. That is what we will be focusing more in the class. Okay. Discrete event stochastic simulation models. So, as we said earlier, the discrete event simulation. So, in our case, we are modeling a system. Okay. The system is studied as it evolves over time. Okay. So, the system evolves over time. So, how do we do that? This is done by a representation. This is done by a representation where the state variables change instantaneously at separate or separated points in time. So, what we are talking here is that we are modeling the system. Okay, we are modeling the system as it evolves over time. And how do we are doing is, we are doing this by representing the state variables, or the state variable changes are represented instantaneously at separate points of time. Okay. So, the things happen as I drew the graph earlier. Okay, as time progresses, the system state is drawn something like this. Okay, as time progresses, it will come down, then it goes up again, then it comes down, stuff like this. Okay. So, such kind of instantaneous changes at separate time intervals. So, if you say this is t equal to 0, this is t1, t2, t3, t4, t5, etc. These are individual separate time instances. Okay. Or in a better way, the simply put, we can say that simply and specifically, okay, we can always say that state change can occur only at a countable number of points in time. So, we are modeling the system where the state change can occur only at a countable number of points in time. So, you can say how many events happened: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can actually count. You can say that here T10. So, 10 events has happened. So, because of this countable number of points in time, you can do this, and these time points are when a particular event, is a new word for you, event occurs. Okay. So, what is an event? An event is something like, if you talk about it, it's a particular happening that. So, what is an event? We are going to talk about it, but remember, if we talked about the bank teller example, people are waiting in a queue here. Okay, 3 people are waiting, and here is the bank teller. Okay, sitting in a chair, and there's a computer right next to it, and here is one person getting served. So, as of now, the number of people in the system is at a value of 4, and let us say one more person came and joined the queue. Then at that instance, that particular time instant, the system state changes, because now the number of people in the system becomes 1, 2, 3, 4 plus 1, 5, and from that time period onwards until the next person comes or the person leaves, the state of the system continues to be in the same place. So, this kind of, when the person joined the queue or when a person leaves, this is what we call as a particular event. So, let us define what is an event. Okay. An event is instantaneous occurrence that may change the state of the system. Okay. So, what we are talking about here is, an event is an instantaneous occurrence that changes the state of the system. So, when I said a person arriving, okay, a person joining the queue, okay, which in another way we can think about it as arriving at bank, Okay. This is one particular instant, that is an event. Okay. This translates to an event. Okay. Event 1. Another example of this is a person leaving the bank. This is another event. Okay. Event 2. Okay. The person can leave. Then another person leaving from the queue. Okay. A person leaving the queue. Okay. This is E3, event 3, like this. So, there can multiple events can happen, and any of those events happening will change the state of the system. Okay. So, that is exactly what is called as a event. So, in another words, sometimes in simulation, okay, specific events are created to make or to facilitate, to make a decision or facilitate a decision about the system's operation, the system's apostrophe s operation. So, sometimes other than the natural events that are happening, you might have to create specific events, very specialized events. So, what are that kind of a specialized events? An example of this will be start the simulation. Okay. End of simulation, etc. So, these kind of specialized events that are created for you to run or facilitate the simulation model or operation of the system is what they are also events. They are not really there, these are can also be not natural events related to the system. Okay. So, hence some people also call this as pseudo entities. Okay. When somebody says pseudo entities, that means we are referring to these kind of entities which are not really natural events related to the system, but is created to facilitate a decision about the system's operation, whether the simulation need to be started or simulation need to be ended, that kind of a thing. Also, the discrete event simulations can be done by hand. There is no rule that you have to use a computer to do it, but it is usually done by a computer. Why? Why do we usually do it with a computer? The simple problem of a single server system, okay, becomes very complex to simulate by hand. Okay. If you are going to do the simulation by hand, be prepared to be there for a long time period, because these are not very easy to do. Okay. So, hence we usually use a computer to do it, but we will do a very small simulation in the class for you to make you understand the various aspects of simulation. Okay. Now, with that we will move into what we call as the example of a discrete event simulation, which is important for us. Let us see what are the major examples that we are going to take. So, as I mentioned earlier, that a single server queue or a single server system is a very simplistic system, but it is quite hard to simulate it with hand. So, a single server system is something that you can imagine this way. Here is a server, okay, S1 single server, only one person is there as service, and the single server can, you can think about it as, can serve one entity. Okay. Now, the question is, what is an entity? We already studied what is an entity. They are the items, things that flow through the system. We already studied that. And there is a queue, okay, and the entities wait in the queues. Okay. These are entities. So, what happens in a single server system is that, an entity arrives, okay, it is an entity arrival, When it arrives, if it sees that the server is free, okay. So, the two questions is server free or is server busy? If the server is free, then immediately go get served. Okay. If the server is not free, then join the queue and wait in the queue, and when your turn comes in, you will be pulled from the queue. So, this is the call for service. So, this is one of the most simple systems that you can see. Okay. So, what is one of the most important aspects of this? Why people study such systems? The main thing is to estimate, or you want to find out, you want to estimate or find out expected average delay in queue. Okay. Or you want to find out how long should one wait before getting served. This is the big question that is to be answered as part of this. How long you should wait before getting served. Okay. That is why you study a system like this. And what are some of the state variables of this? The major state variables include, okay, one is the status of the server. Okay. There are two options in front of this. One is idle, or what you call as free. The other one is busy, servicing someone. Okay. So, you need to know this during arrival, because if free, then go and get served. If busy, wait in queue to get called for service. Okay. So, the server is free, then you go and get served. If the server is busy, then wait in the queue to get service. So, this is important for you to know when an entity arrives into the system. So, this is one of the state variables. So, then other aspect is current length of the queue. Okay. You need to know this because decides whether to wait in the queue or leave without being served. Sometimes when you actually go to a place and see a very long queue there, then what people do is that people sometimes say, oh, I am not going to be here, I will leave and I will come back later. Okay. So, such kind of a decision happens. For that, you need to know what is the length of the queue. Then another state variable, these are not all the state variables, these are few examples what we are talking about. Okay. Now, the third one is the time of arrival of each customer into the queue. Okay. This is required to decide when to start the service, also it helps you to identify how long the person was in the system. If you want to find out how long the person or how long the entity, you can think about person as a entity. Okay. How long the person or the entity was in the system is another aspect that is related So, these are few examples of the state variables of the system that tells you how the state of the system or how the system state behaves. Okay. Similarly, about events. Okay. Events, some of the major events are arrival of a new customer, so when an event happens implies system state changes. Okay. So, when a new customer arrives, then the number and the people, number in the queue, everything goes up by 1. Okay. Then service completion or departure of a customer. So, when the service is completed and a customer departure from the system, then that is also, it will reduce the number in the system. So, here it will increase the number in the system. In this case, it will decrease the number in the system. Okay. Then you can also have end of simulation events, or you can think about it as pseudo events. Okay. This is helps to make modeling decisions. So, if you say that I want the bank to simulate for 8 hours, if you say study for 8 hours, which is equal to 8 into 60, 480 minutes. So, you say that okay, the clock keep on ticking, and as soon as you reach the 480 minutes, stop the study. Okay, stop study. When this happens, then you see the reports and other things. So, this is not a actual event, it is a pseudo event which allows you to do the what we call as the modeling decision of the system. Now, also the other major thing that we also need to do is how is this time being kept in the system. Okay. This is a important aspect of the system, because the time keeping mechanism is quite significant for our work. Okay. So, the first thing is what we call as a simulation clock. Okay. So, what is a simulation clock? It is simply a variable. It is a variable that keeps the current value of the simulated time of the model. It is not the real time that we talk about, we are talking about the simulated time. The time is a simulated time. You are not going, if you are going to study the system for 8 hours, that means, that does not mean that you stand in front of the computer for 8 hours and observe it. The simulated time is way faster than the actual 8 hours. That is the reason why you use simulation. Okay. So, this actually variable that keeps the current value of the simulated time of the model. What it does is, the modeler must decide on and be consistent, about the time units. So, if you say that I am going to study the system in minutes, then stick with minutes, do not keep on changing things here and there. Okay. Ideally, there is no relationship between simulated time and actual time. Okay. So, that means this is necessary to run or simulate. When you use the word run, it is also equivalent to simulate. the model on a computer. Okay. So, you are having what we call as the simulation clock, a variable that keeps the current value of the time, and the modeler must decide on initially and be consistent about the time units, and there is no relationship between the simulated time and the actual time, and you require this because you want to literally run the model on a computer. And there are two approaches, two typical approaches are used for the advancing the time or to do the time advance of the simulated time. Okay, you are talking about the simulated time. How are we doing this? Okay, the first one is the next event time advance. Okay, you identify what is the next event that is going to happen, and then do the time advance. This is the most commonly used approach. Okay, this is one example. Next one is the fixed increment time advance. Okay, that means the clock will advance by every 5 minutes, and then the system states are measured at every 5th minute. Okay, this is seldom used, not very common, but this is typically used in sometimes in studying traffic systems like traffic flows, etc. Okay, but not very commonly used. Okay, the most commonly used one is the next event time advance approach. Okay, so with this, what we will do today is that we will stop today's. Actually, we will continue with one more slide, and then we will stop after this. This is the we will talk about how the next event time advance work, and then we will stop today, and then we will come back in the next class. So, what happens is, how does the next event time advance work? So, first what you do is you initialize a simulation clock. You initialize it to 0. Okay, that is the first thing you need to do. Then, so you start with the time t equal to 0. Then determine times of occurrence of future events. Okay, this is called building the event list. Okay, so you are here to build the event list. So you build the event list, and from there you determine the times of occurrence of the future events. Then what happens is clock advances. Where does a clock advances? To the next or the most imminent event. Okay, that is to be executed. So, you advance the time to the next or the most imminent event to be executed, and this involves updating the event list. So, what happens is you remove it from the event list, and then once it is executed, you remove from the event list, and then next one comes up in the higher in the order, and then continue until how long will you continue until stopping rule is satisfied. Rule is satisfied. Okay, and stopping rule should be explicitly stated. Should be explicitly stated. Okay, so that is the continue until. Then clock jumps from one event time to another next event, that which means the times between the events do not exist. Okay, which means we are only in the period of inactivity is ignored. Okay, so implies if no event happens or no state change, time is skipped. Okay, so this is how the time gets managed in the simulation. So, hopefully, this has now make you understand that how the and when you do an example, a complete example, then you will get a clean idea of how to do it and go from there. So, hopefully, you guys understood the more advanced or internal modules of the simulation and how the inner workings of it. And in the next class, we will do an example, so that the concepts becomes crystal clear to you. Thank you for your patient listening, and please read the textbook so that you can be updated on to the concepts. Thank you very much.